Welcome to AP Podcast 10.2b. This is a continuation of what we've done before when we were talking about vapor pressure and all that. Now we're going to look at changes of state and the heating curve that you get when that occurs. And so if you take a graph and you go through all the you start at a solid, you go through all the changes that occur, we call that a heating curve. And then here's something you already know. When a solid turns to a liquid, we call that the melting point. Now the energy to accomplish that, and here's another delta H. You're going, wait, how many are there? Well, there's a lot. The energy to require that is called the heat of fusion. Look for the FUS there, or enthalpy of fusion, depending on how you want to say it. All right. So let's look at a simple heating curve for water, because it tells us quite a bit. So we're starting at a negative 20 degrees Celsius down here, all right? And we've got a beaker of ice. Now I start pumping in heat, okay? And what happens is that heat causes the ice to actually warm up. So the ice warms up and it gets to 0 degrees. Now what happens at 0 degrees? Well, at 0 degrees we get melting, right? Since we're going up, we get melting right here. And so notice what happens to the heating curve. The level plateaus. Now, why in the world would it do that? I'm still adding heat, right? So why in the world would that happen? Well, think about the molecules. Right here in ice, I've got a solid. Okay? Now those molecules are locked in that lattice and they're vibrating and moving a little bit, and the heat is causing some of them to eventually start to escape. So then when we get to that point where we can start to melt, all the energy that is going into this in the form of heat is causing the melting. So what it's doing is it's taking those bonds, those intermolecular bonds between the ice crystals, and it's causing them to break up, so that we get individual water molecules, all right, in the liquid state. So all that's occurring. Now at this point, we have all the ice gone. And now we're still heating, we're adding heat, right? Now notice the temperature of the water is going up, okay? So all my ice is gone, it's 0 degrees Celsius, and the heat causes the water to go up. And then look, we get to another plateau at 100 degrees Celsius. By the way, this isn't labeled and it should have been. This is temp, and this is time over here. Alright? So then we get a plateau. Now ask yourself, what's going on here at this plateau? Well, we're taking the water in the liquid state right here, and now we're causing it to, the energy is to turn it to steam. Okay? So now we've got water vapor, right? Particles are very far apart. So all the energy that's going in, because again, we're still heating this thing, all the energy going in there is causing the water in the liquid form to overcome the intermolecular forces and go into steam. And then once every particle is now steam, now we can get the temperature to go up. So it's a really important thing, and you've got to be aware of what those 2 points are, those 2 plateaus. And we do have a name for them. Here's a graph right here. So at this point, this is called the heat of fusion, and then up here is the heat of vaporization. Now again, we've got a couple things. We've got to be aware of which way we're going. Oftentimes, at this point, we're going up the scale, so it's melting. But if we're going down the scale, what's going on? Freezing, right? And then right here, we've got this boiling. But if we're coming down, we've got condensing. All right. So there's a heating curve for water. And those 2 points are very important. You've got to be very aware of what is going on as far as the energy involved and intermolecular forces and what you're overcoming. So let's just look at those two terms a little closer. The melting point is determined by the vapor pressure of the solid and liquid. This is something that is kind of hard for students to wrap their head around, but you've got this solid, and it does have a vapor pressure. All right, it does have a vapor pressure, and depending on what kind of solid it is, that they'll vary from very little to quite a bit actually. But what happens is when the vapor pressure of the solid equals the vapor pressure of the liquid, that's when we can get those molecules flowing and get to the liquid state. All right. Now boiling point, a little bit different. Boiling point, we've got a liquid, and when we get the vapor pressure of the liquid equaling the atmosphere, okay, the surrounding atmosphere, that's when we get boiling. Now, the normal boiling point is 1 atmosphere pressure, and here in Tacoma, we are, of course, at 1 atmosphere pressure. But my wife's family lives in Denver. And there, I don't know what the pressure is, but they're 1 mile high, roughly. Okay, so let's just say the pressure is 0.96 atms. Okay, so what that means is that the water to boil only has to get to 0.96 atms before it can start boiling. Now, as far as temperature goes, that occurs at a lower temperature. So where in Tacoma we'll boil water at roughly at 100 degrees Celsius. In Denver, maybe we're only boiling water at, let's just say, 98 degrees Celsius. And so what that means is when you boil an egg, you got to heat it a little longer because the temperature is not the same. Kind of an interesting fact there. And if you were to go to somewhere like Mount Everest, man, it wouldn't take very much energy to boil water at all because the atmospheric pressure up there is so much less than the vapor pressure of water. Okay, and this is why if I get a chance, I'll go ahead and boil water at room temperature in a vacuum chamber for you guys. Okay, now there's 2 more terms here, and these don't show up on AP, but they're kind of interesting. Superheating, right? This is what happens when you get a liquid to get hotter than the boiling point. And sometimes this could be a real problem if you're boiling water in a microwave, because that water can get hotter than normal. You grab the beaker, hotter than normal. It could get above boiling. You grab the beaker and just shake it a little bit, and then you get a super bubble to just go, and boiling water basically goes all over the place. But it does happen. And then supercooling. So imagine if I had like a graph here, and we were looking at the normal cooling point of water, and it's cooling down, and right here we get ice, right? Well, sometimes with supercooling, you cool it so fast, the temperature drops below here, and then goes like that. So that happens every once in a while. In fact, we'll do a lab where we'll try and get water to supercool a little bit. All right. So those are 2 more terms. Again, they don't pop up on AP very often, but it's kind of interesting. And if you hear about superheating or supercooling, you can at least have a feel for what it means. Okay, so let's look at the kind of problem we might have to do here. Okay, substance X has the following properties, and then it's important that we know what these terms mean. All right, there's the heat of vaporization. That's what energy it takes to boil the water, right? Here's the heat of fusion. That's the energy involved when you're going to freeze or melt a mole of water. And then here are the boiling points and the melting points, and right here the specific heat capacity of each one of those. So what I'd like you to do is just take a moment and sketch a heating curve. I'm going to do the same, and then we'll see if ours match. Okay, so here we go. If you look at the diagram, I'm starting at -50 right here, right? And then the melting point's at a -15. And look how much energy it takes. It only takes 5 kilojoules per mole. So what I did is I started at 50, went up to about 15, and I made this kind of short because it's only going to take 5 kilojoules per mole. And remember, we're adding heat constantly here. And then I'm going up to, for the next thing, the boiling point is at 75, and that takes 20, so I'm going to make that a little bit longer. Whoa, those are nice circles. And then So I went on up and then went straight ahead, and then last but not least we went up there. Okay. Now how would I use these other numbers? If it wasn't a sketch, what would these numbers mean to me? Because this is important stuff. All right. Look at the specific heat capacity for the gas. It's lower than, oh, I like this new thing here. Okay. And then the liquid, and then the solid. It takes more energy per gram to heat up the solid than the liquid and the gas. Okay. So hopefully, what would I use that for? Well, I imagine you might use that for these lines, and I probably didn't do a very good job on that. Maybe this line, because it takes more energy, this slope should be a little bit flatter. Okay. And then this slope should be a little bit flatter. And then this slope should really be a little more straighter, if I was going to really look at that. Okay? So we'll do some problems with this stuff. Heating curves are pretty fun to mess with, and there's some really interesting calculations we'll do in class when we come back next time. See you later.